Okay, this is the second screencast with the ideas of using motion diagrams or oil drops or other types of physical representations to track the motion of objects. So here in the upper one we have two drop patterns. So two cars moved, they had a drip of oil coming out every so often, and they left these patterns behind. We have 6 possibilities we want you to see. From the diagram, what can we say about the car? Now, first of all, be careful. You can't read too much into your oil drops. First of all, there's nothing telling us which way the cars are moving. They may have been going this way, or they may have been going to the left. That would determine whether they're getting faster or slower. Right, so we can't necessarily say faster or slower, but if there is a change in the spacing, and we're assuming the time intervals are constant, we can say that they are undergoing a change in speed, which would then be an acceleration. So if you look at the first one, if you look at this gap here and compare it to the gap over here, there is clearly a large difference between the two. So the gaps, distances between two dots are changing, so therefore this must have acceleration. This one, again over here, it's pretty large, and this one, it's even smaller than the one above. So yes, we can say it's undergoing acceleration. Okay, so both cars have constant velocity. Well, by definition, if they are accelerating, and since acceleration is the rate of change of velocity, you can't have both. And we know they have acceleration. Both cars have an accelerated motion. Yes, we can say that. They are either getting faster or slower. Okay, car A is accelerating, car B is not. We can't say that. We said they were both accelerating. Car B is accelerating, car A is not. Again, we can't say that. We know they're both accelerating. Now, E is tricky. If we know when the drops occur, we might be able to tell which one's acceleration is greater. But again, we have no information telling us how much time is in between each drop and whether the times are the same for both diagrams. One might have a leak that's very rapid, the other might have a leak that's kind of slow. So we can't say with any certainty which one's acceleration is necessarily greater than the others. Plus the pictures really, if one picture is really definitely different, we might be able to take a pretty good shot at it, but they're pretty close. Okay, number 4 deals with the vector nature of acceleration and velocity. The motion, the velocity is to the left. Right now, so that means we started here. As we move, we should notice the spacing is getting smaller. We're covering less distance for every unit of time, so that means we're getting slower, so our speed part of velocity is going down. So as we move to the left, we're slowing down, which indicates that our acceleration has to be against our motion, so that must be to the right. So velocity is to the left, acceleration is to the right. So it has a leftward velocity and a rightward acceleration. Now, neither of those is 0. Perhaps the velocity is 0 here at the end, but we can't say that during the entire motion. So it's leftward and rightward. Motion to the left, acceleration to the right. Alright, so we're going to try to match the statements below with the pictures left behind. 2 key spots. Anytime you see this group like several drops in one place, that's an indication that during that time our person or our car has stopped. Okay, so here are the traces, and we're going to try to match those up. So we're going to look for places where it says rest. Here's a rest. That's probably going to be either C or A because they both have signs of rest. We'll have to figure out which one it is. Slow constant speed, went to rest, remained there for a while, so there's the big drops, and then drove very slowly at a constant speed. So we need something that slows down and then moves away at a constant speed. Well, let's come back to that one. Renata rapidly decelerated from a high speed to a rest position. So again, we need rest. So again, this is going to be between C and A. And then slowly accelerated to a moderate speed. So we're going to need something where we see the pictures getting closer together and then farther apart. So closer together as we come in this way, stop, and then farther apart. Okay, so it says moderate speed, but that seems to be reasonable. So I would say that's A. Now that's going to indicate this is C, so let's see if that works. Driving with a slow constant speed, they're pretty close together, so that's not very fast. Decelerated to rest, slowed down and stopped, that's where we get the big oil drop. And remained there for a while, and then drove very slowly to constant speed. Now we can say that's very slowly because the pictures are very close together, and they do appear to be constantly or equally spaced. So we're going to call that one C. And then finally, Renata was driving at a moderate speed and slowly accelerated. So let's see if B matches that. Driving at a moderate speed, so we're looking at gaps that are equally spaced but not too wide. And it says accelerated. Now, slowly accelerated could mean get faster or get slower. So we're looking for a increase in the gaps or a decrease in the gaps. And if you start to notice right about here, we start to get a slight increase in the gaps. Okay, now this is not really good terminology. Slowly accelerated, it seems to imply that acceleration can be fast or slow. It's not really the best way to think about it. Typically we think of acceleration as high or low, large or small. With a large rate of acceleration, your velocity will change very quickly. With a low or small rate of acceleration, your velocity will change much more moderately or slowly as it happens. Be careful mixing the words slow and fast with acceleration. They are not, they don't mean the same thing, and it's very, very easy as you start out to confuse velocity and acceleration. Velocity is what you see. Most of us are easier, stick with the visual easier, so you tend to confuse acceleration with velocity, so be careful about that. Okay, so that's one of our three ways that we track motion, through a motion diagram, or looking at where the object was located in positions in time. We also use position time graphs, and we also use mathematical equations at this point. We'll later on be looking at velocity and acceleration time graphs as we go forward. And that's it for this version of our study.